Subir Chowdhury School of Quality and Reliability, IIT Kharagpur, and patrons of this series, Director IIT Kharagpur, Professor B.K. Tiwari, and the CEO ASI Consulting, Sri Subir Chowdhury, the members of the advisory committee of this school, and one of the member I'm saying, Commander Jetli, who is also moderator to question and answer. Our head, Professor Pradhan, and of course, guest of this evening, Professor Modarres, who is going to give the lecture on fundamental sciences of reliability. And the audience, our students, our research scholars, I welcome you all this specious evening. We have already started, as you know, that the series on 15th of January, and this is the third lecture in this series. Future, you will also see the people like Professor Modarres, who are authority in the area of QRAMS. This is all I want to say, and request Professor Aaron Rai to read a brief bio of Professor Modarres to start this lecture. Thank you very much.
Thank you, sir. Good evening, ladies and gentlemen. Dr. Modarres is the Nicole Y. Kim Eminent Professor of Engineering and Director, Center for Risk and Reliability at University of Maryland, College Park. He is expert in reliability engineering, probabilistic risk assessment, physics of failure, and fracture mechanics. His interests in risk, reliability, structural integrity, and prognosis and health management include both experimental and probabilistic model development efforts. He has over 450 papers in archival journals and proceedings of conferences, including multiple textbooks and book chapters in various areas of risk and reliability engineering. He is a University of Maryland Distinguished Scholar Teacher and a Fellow of American Nuclear Society. Dr. Modarres received his BS in Mechanical Engineering from Tehran Polytechnic, MS in Mechanical Engineering from MIT, and MS and PhD in Nuclear Engineering also from MIT. Before I hand over the dais to our distinguished speaker, I would like to inform the audience that they can raise questions through the chat box. The moderator, Commander Jetli Saab, will then put forth the query to our speaker. Our moderator has the last say on the selection of questions. May I now request our distinguished speaker to start his presentation, sir.
Thank you very much. Good evening. I would like to thank the IIT Kharagpur in India, the QRAMS group that made this invitation to me. It's been a pleasure to give this talk tonight. So my talk is on the fundamental sciences of reliability, and I tell you why that I picked up this this particular topic. Before I start, I'd like to just say that this talk would have not been possible without, of course, a big team of my former students, postdocs, and of course, colleagues at the university. I always appreciate their contribution. We professors without students are basically very little or nothing we can do. So that's always appreciated. So why did I pick up this? The reason is because always this question has been risen in even when I was a student myself, as a graduate student, studying also risk and reliability, that whether or not reliability engineering is a discipline in engineering. Is it a discipline of statistics, or is it a discipline of operations research? A lot of actually engineering faculty, they said that probably your topic of research belongs to statistics or operations research, not engineering. So that always concerned me. Of course, then, so the question has always been in my mind that what is engineering? Well, from Webster's dictionary, engineering is defined as the application of science and mathematics by which the properties of matter and sources of energy in nature are made useful to people. So the key words here are these applications of science and mathematics. I don't think that anyone was disputing the fact that reliability engineering is using a lot of mathematics and is an application of mathematics, but was it an application of physical sciences? Does the physical sciences also plays a role? So that was always the question. And so I went, and of course, if you look at what is the statistics of course is the collection of an organization and analysis and interpretation of masses of data and numerical data and numerical analysis of data. So generally everyone agrees that that's a subfield of engineering, therefore it is part of this. The mathematical part is already known, and it's already definitely is a part of mathematics. No question about that. But what is it part of operations research? Maybe the discipline of operations research is that one that deals with the development and applications of advanced analytical methods to improve decision making. Of course, we use also some decision making, but that's not necessarily the prime objective or thrust of a reliability engineering, but nevertheless we do those kinds of things. So yes, it does partly belong to this, but not totally. But the main question still remains, is it a physical science or is it not a physical science? So in this talk, I'm going to be trying to answer this question. If reliability engineering is a legitimate engineering science, then what is the fundamental sciences that underpinning its theories and methods in physical sciences, of course. So reliability engineering essentially is formally essentially defined as a scientific know-how. This is a known definition of reliability to a component, product, plant, or process in order to ensure that it performs its intended function without failure for the required duration of time within a specified environment. Okay, so this is well known. So the key to it, again, I have highlighted here, is without failure. So the question is where the failures come from. Of course, the statistics use mathematical methods to find the frequency at which we see these failures, but doesn't define what is really the foundational reason that this failure comes. So therefore, the question is what is physical science where it defines this failure? And we know that failure comes from the damage. This damage is either damage that actually occurs cumulatively or because of some kind of an over-stress condition that ultimately leads into a material damage and a failure. So how can we explain those from a physical sciences that we could define reliability engineering from that perspective? So one can say thermodynamics is and that's essentially my talk today would be that the thermodynamics essentially is the fundamental underlying physical sciences that supports and founds the reliability engineering. So let's look at this described material. Essentially, we can, through thermodynamic, describe the material cumulative damage over stress, and that can be done within the irreversible non-equilibrium thermodynamics. We can do that also through the statistical mechanics definition of second law of thermodynamic, which is entropy, and also through the information theory, where information entropy is also possible to define the damage. So therefore, the damage and failure can be described within these fundamental sciences, which is undisputably a foundational science which exists today. One of the probably the most, I would argue that thermodynamics is probably the most undisputable science which exists today. And it could enhance, of course, these methods that we learn from thermodynamics could also enhance the present trends in reliability engineering, which focuses on prognosis and health management of structures and components. So application of thermodynamics in reliability engineering, of course, is not new. So I don't want you to believe that I offered this as the first person, but actually it has been offered already in the past as possible definition. But of course, I have described it, I've tried to describe it as a foundational science of reliability and enhance it through my research a little bit further. So where is the thermodynamic essentially can be defined? Of course, we know, most of you, if you're mechanical engineers, you know that the second law of thermodynamic describes that in an isolated system, entropy will always increases until it reaches a maximum value. And I would show you that that maximum value in materials and in components would be the point that a component fails. This definition was given by Rudolf Clausius, a sketch of whom you would see on the left. And here he was the first one in the late 1880s that described this law. And later on, in the late, again, a few years later, Ludwig Boltzmann, one of my heroes actually, he defined the same second law of thermodynamics through the statistical mechanics, which essentially indicated that in an isolated system, the system will always progress to a macro state that corresponds to maximum number of micro states. So if I give you a little bit of what this really means in terms of reliability, it means if you can look at reliability as a essentially micro a system as a micro or atomic collection of a lot of atoms together, you can see that always there are some problems or some disconnects occurs in the atoms that ultimately leads to fractures, and that's how you can say these micro states, being, for instance, crystals and things that are on micro level inside the system, can grow into a macro state, which is essentially going to cause which is going to cause the failure ultimately. So this progresses that, and I think in statistical mechanics, always this is described as release of gases inside a volume. So if you have a compressed gas, and if you release it inside a volume, the molecules of gas essentially disperse, and it can disperse in many different ways. But ultimately, it goes to the maximum number of dispersion that it can get is the value of the maximum entropy that you can see. So therefore, there is a very close relationship between damage and the second law of thermodynamic. And we could say that all damages occur due to some failure mechanism in materials that leads into failures, which we call in reliability, as you saw it, my definition, an important time that we try to find and quantify and predict. And that failure mechanism can be caused by environmental or operational conditions or overstresses that could lead to a failure. And all of them have one common feature, and that is dissipation of energy. They all dissipate energy. In other words, the content of energy of materials is released as the component undergoes damage. So dissipation is a fundamental fundamental determinant of irreversibility in thermodynamic, which describes within and can be described easily within the non-equilibrium thermodynamics. So how that can be done is what I'm going to say in a very soon. So let's look at actually how reliability has been dealt with so far. Just give you a quick history before I delved into a little bit entropy and thermodynamics. In the past, we always, we know a failure occurs at one time. So we looked at that failure and we fit a distribution to that failure. That was the historical and is, in fact, in a lot of places still the use of reliability engineering. Look at the times of failure. History essentially tells us what failures occur, and we say always history repeats itself in the future, and therefore we can say in the same things happen. Unfortunately, this definition hasn't been very good because we always see that the past is, especially in reliability, has not been always a good indicator of future. And we see components that we test them in the lab, we see them in the field, would not essentially behave the same in the future. So in order to alleviate that, the new trend in reliability came in the 1960s, originated, and then picked up again in the 1980s as a physics of failure, which essentially followed markers of damage. Essentially what it did, it took out these physics as failure mechanisms and put an empirical model on those that have, for instance, fatigue or a corrosion accumulate damage, and finally how much that damage has, how much a component has endurance over that damage, and once that endurance is reached, a failure occurs. So instead of that distribution, it follows the amount of damage from time zero based on some empirical models. And then once it found a level of endurance, then you find the times of failures from those points. And then a distribution is built based on those points rather than the historical data that we gathered from the past. And that gave us a little bit more controlled way of finding the damage and a little bit better controlled way of predicting future behaviors by increasing, if we are at any point in our system, we can predict when it reaches the level of damage, the level of endurance. That has been a very important and good progress, and gave us a bit of more comfort about the estimate. So where the future lies is that, based on my talk here, is that essentially instead of these following markers of damage, which often occurs actually after a lot of damage is accumulated before you see markers such as crack, such as amount of corrosion or release of materials from corrosion or wear, those are markers. We could actually use thermodynamics before you see even anything. And those are the kinds of things PHMs are very much interested. And look at actually measure the dissipated energy, and before you see any measure, and then try to find out what is entropy, which is generated, and find out how much entropy to failure or entropic level of entropy exists, very similar to this, how much damage you have. And then once you reach that, you develop a distribution here of amount of entropy which is accumulated, based on which we can convert this distribution into the distribution of time to failure. A much more elegant, much more powerful, and it can start actually modeling from very early on. So why do we use entropy? Entropy is an independent of the path to failure. So we could always say that it very much depends on how much stress you put. But once the entropy reaches this level, regardless of how it reached it, if it reached it through a quick path to this level or a very slow path, once it reaches this level, a failure occurs. Therefore, entropy is independent of the path to failure. Entropy accounts for complex synergistic effects. So when I have entropy of corrosion and entropy of fatigue, both of them have the same measure, which is entropy. It's not like the physics of failure, which markers of damage are very different in crack and very different in corrosion. In the entropy is the same for corrosion, is the same measure for fatigue, is the same measure for wear, the same measure for creep, fretting, everything. The other thing which is very important is entropy is the scale independent, meaning that you could start from a micro level, actually atomic level, measure the amount of entropic accumulation and measure it to the point of end. So therefore, I come to the next definition that I say that failure mechanisms cause damage. Damages generate as they move on. They do dissipate energy, and then they generate entropy. And once entropy reaches a level, it fails. So we say failures occur when accumulated entropy reaches a level of entropic endurance. And I say entropic endurance describes the capacity of a unit, being a material, a component, a system, to stand accumulated entropy. Entropic endurance is identical for identical units. It is different for different units. So if I have component A, which is completely different than component B, the total cumulative entropic level that causes its failure could be different from another one. Entropic endurance to failures can be measured mostly for now experimentally, and it involves, of course, stochastic variability, because material are stochastically variable. Therefore, entropics that they have also very different. At the end, the entropic of different components of the similar components could be slightly different even because of its atomic micro level structural variability that exists. So we can also normalize damage by finding the entropy at each point minus entropy at the time of failure, and then this is the entropy at the time of failure minus entropy at time zero. So this is entropy at time zero. Entropy, this is a brand new component, entropy currently, divided by the entropy at the time of failure minus entropy at the present time. So with that, we can, how do we calculate the dissipated energy? So the dissipated energy is very similarly, very well developed in thermodynamics. In non-equilibrium thermodynamic, essentially defines amount of entropy generated as a force, as a force X, and as another variable called flux J. And it happens that flux is also is dependent also on force. So, but generally, this entropy generation is a function of this flux and force. Later on, actually, and this is very important. Later on, actually, Lars Onsager, a professor in Yale, for which actually for this finding, received Nobel Prize in Chemistry, said that there is a reciprocal relationship in this J, and found this relationship J as a function of X, and defined it in this way, that J of, for instance, corrosion is a function of an L, which he defines it as a coefficient, of Onsager phenomenological coefficient, which can be calculated experimentally, of the force of, let's say, corrosion and force of fatigue, if this is a fatigue and corrosion, and these are the L's are these coefficients, which essentially should be found. So let's say if you have only corrosion fatigue, this matrix is a 2 by 2 matrix of the phenomenological of corrosion on corrosion, or corrosion on fatigue, or fatigue on fatigue. And therefore, each of them can be written in this form. So what is the importance of this? The importance of this is that when we have a lot of these phenomenological aspects in reliability that interact with each other, such as corrosion fatigue or creep fatigue, then these can be well defined. And this has been really a sore point in reliability in the past, because we had difficulty modeling them properly. And now entropy allows us to do that very smoothly and nicely. I won't dwell a lot about this equation. This is, of course, in some of my papers, like what you see here, or some of other people's work. You can see it down here. We have defined it. Generally speaking, any phenomenon of cumulative damage has these components: a thermal component. So if you're fatiguing, there is a heat element that actually is generated. That's one dissipation of energy. The other dissipation is diffusion of energy. For instance, hydrogen diffusion, hydrogen embrittlement, all kinds of, let's say, the electron migration. All of these are diffusion in nature that causes failure. There's also a plastic deformation. The famous element of it is fatigue. For instance, deformations of those sorts. There's a chemical reaction, which essentially a lot of corrosion phenomena can be defined like this. A lot of external field energy damages. These are like something drops and fractures. These kinds of terms can describe those kinds of phenomena. And the only idea is to see what is the force and what is the flux of these. For instance, in the heat conduction, the force is the temperature gradient. The flux is the flow of heat, Q. Let's say volumetric flow of heat. We can easily describe the fatigue, creep, and where has these elements of heat conduction that can be measured. We have plastic deformation, such as stress and strain, which in, let's say, fatigue and creep and wear, we can find them and measure them easily, and therefore dissipated energy can be found. I won't go through all of them, but again, we have in this paper in the past, this is in journal Entropy, this has been defined what these forces and fluxes in reliability are that causes the damage. So if I look at actually a few of these, if you look at dissipated energies, as I said, thermodynamic, I just showed it one way to describe it, but it's not the only way. You could actually also use the statistical mechanics and find the entropy also, which is this form. Of course, some of our past papers have focused on this. The Jeffreys diversions in finding entropy, statistical mechanics entropy. The difference is that you just find the dispersions of the material rather than the thermal impacts or thermal dissipations, such as the thermodynamic, such as this thermal force of stress and strain together. Also, you could find in data such as in information that you get from damages such as acoustic data, if you have dissipation such as acoustic energies dissipated, you could use the information entropy such as such as the Shannon entropy law, which is you see it here, to calculate those dissipations. So generally speaking, in all of these methods, if you look at, for instance, just the stress and the strain, this is the hysteresis loop, which is famous. You go from point A to point B as you apply a load which causes damage, and when that load is removed, you get to B. So this load did happen in, let's say, aircrafts flying, and it sees all these damages, these loads up and down, causing these cycles of damage. Each cycle, the area inside the cycle determines how much energy is dissipated. So all we need to find is how much stress we put, how much strains we saw. We can calculate the amount of energy dissipated, and that gives us how much damage we have accumulated. Similarly, we could use in statistical mechanics, it uses the forward and backward energies, and these equations are because of that forward and backward energies generated, where then we use the Jeffreys diversion to calculate actually the entropy. And then finally, we use for acoustic data, we use acoustic emission. So let's look at just one example of acoustic emission data. Here's one data generally came from a damage we are simulating in one of my labs. Each of them, note here that this data are in milliseconds. So in a one millisecond, you see this kind of a wave, and this is known as acoustic signal, or as a wave, acoustic wave essentially. And if I can easily convert this wave to a distribution, find out the sizes of these from plus to minus, and put them into a distribution function. If I put it into this distribution function, then the Shannon entropy allows me to take this P of xi is this distribution, and log of pi is the log of that distribution. It can be converted easily into the entropy. So if you look at this on the side, at each signal, each of these wave forms transformed into one of these dots in this graph. You can see this is the amount of entropy as the time goes by, as we are adding more and more damage to the component. And if you look at this thing, you don't see anything. You just see a bunch of dots. You see a little bit darker area here. But if you average them over the length of time, if you take and average them over a certain period and find averages, actually you see an increasing entropy. You see the entropy is actually increasing because of this damage. So that tells us the information entropy increases, which then correlates closely with the damage. So here's like a one result of that entropy. If you look at the entropy here, this x-axis shows the actual damage, which is measured in observable marker of damage, such as the crack length. This is the point that the component fractures completely. This is a fatigue test. And then the lines that you see here is what the entropy is predicting as to the amount of damage. And each of the lines is because of a different experiment. You can see, as I said, the entropies have also variability, but they go precisely along the line of failure. Ultimately, they predict a failure accurately at the end. It shows, and these variabilities are understandable because, as I said, each component, even though if they are from the same manufacturer, same process, because of the microscopic differences, they exhibit different progression of cumulative damage. So with that, this is another formula which shows the relationship between two different entropies of corrosion and fatigue. Each of the terms of this is the amount of energy entropy generation, and this shows the force and the flux of each of them. They are all defined here. For instance, the flux is measured by the over potential measurement. Essentially, is the potential in an oxidation, in an electrochemical dissipation and oxidation. We can always measure the amount of current and the amount of flux very easily. And each of these terms shows the amount of flux and the amount of the potential to the current and flux, and then we can calculate the amount of energy dissipated. This term shows the amount of mechanical dissipation. This shows the embrittlement, any hydrogen embrittlement that we have, and this term here. Okay, so generally speaking, this is the equation for a corrosion fatigue, the thermodynamic equation of corrosion fatigue, which interrelate with each other. And this is an example of one of my laboratory testing labs, which you see here. I'm fatiguing. I do experiments also. As I said, I'm both experimental and theoretical person. And here there's a sample right here, which these very powerful digital image correlation cameras are actually finding the amount of strain in them, and the stress is of course measured by these amount of force which this fatigue machine is applying, and you can see it here, but this area right here is this area where corrosion occurs, and these devices here are essentially the electrochemical corrosion which we are measuring through what is known as a gamut potentiostat. So the data from here is measured how much current and how much potential exists inside the area where the crack is happening. And so all in all, every element of the equation I showed in the previous equation is measured. Corrosion occurs because the material is an aluminum, which is used in aircraft structures, and we are corroding it by sodium chloride, a 3.5% sodium chloride. And here's the specimen that is being corroded. Here's the area that actually causes the damage. And then there are 16 samples that we tested. This shows for corrosion results. It shows the potential and cycle. So as I said, the hysteresis loop inside each of these shows the amount of corrosion damage, and area inside here, it shows the amount of the essentially strain energies which are dissipated. And sum of the two. Note here that both of these translate to the same measure of entropy, okay? And they can be summed very easily. The cumulative amount of the two damages can be summed as I'm showing it here. So this shows the hysteresis loop of the corrosion. This shows the corrosion voltage measured. This shows the current. You can see the inside. The graph has an area inside which is very tiny, but that's how much of the energy dissipated. For fatigue, it's a little bit more significant. You see the strain increases, goes to this point and comes down. Again, this shows one cycle of load, and in the area which is confined inside is how much of energy is dissipated, which then turns into damage. So once that happens, I can sum these two together into one unit, and that is called entropy unit. Entropy unit is measured in the megajoules per K, per degree K, Kelvin degree, per unit of volume, okay? So both of these energies, being either corrosion or fatigue, they can be summed together. Here are those 16 tests. Each test were different. We used different chemicals, different forces. But you can see here that they end up to about reasonably the same level of entropy accumulated level that a fracture occurs. And that is around 1. Sorry, this is actually the time that a very tiny crack initiates. This is a tiny crack which is about 250 micron, which actually this is not the time of fracture. This is before that, because we didn't want to go to the time of fracture. Although I have other papers, quite other papers that actually go to the point of fracture. This is actually more accurate to do the point of only the tiny start of a crack that usually is the point that physics of failure starts modeling. This is before a physics of failure can model. So this is a point that actually a crack of this size in an aircraft is really unreasonable to have, because it can, and usually by this time 80% of the life is consumed. So this is very important. This is the point, and you can see the variability is more. Of course, at the point of fracture is around 4, by the way, for fatigue. 4 megajoule per K per cubic meter. But then the data are there are less variability once it reaches this point. If you look at actually then the amount of damage which are accumulated over time, each of these curves show the cumulative damage accumulation from time 0, which of course wasn't completely 0, because some of the units had already some damage to start with, but ends at this the normalized value of damage. Note here, everything is normalized to this point. So the damage starts from 0 and ends at 1. 1 being the point that a crack of 250 micron has been observed. So there are 16 experiments here, and then you can see the results here. Some of them actually we have to stop them ahead of time because of experimental issues or other reasons, but nevertheless, the reason you see the difference is, of course, the loading are different and the chemical compositions are different. So some of them very quickly damage, some of them takes much longer to damage. But they all damage at this. They arrive at this point at this number of time or cycles. For this unit, it arrived earlier because the stresses were higher. For this one, it arrived much later at many more cycles of loading because the loading was more benign. And so that shows. So these are some of the results. And if I were to actually show you the normalized the contribution from that came from amount of damage due to corrosion versus due to fatigue in a corrosion fatigue phenomenon, you can see that for damages that were very high in the amount of stress, more damage was contributed to entropy. You can see that about 90% of the damage, which is 90% of actually the entropic damage, I would say the entropy accumulated, was attributed due to fatigue. But then if the loading was small, which then gave much more time for corrosion to work, because corrosion needs time to act and cause damage, then contribution from corrosion started to getting bigger when the loadings were smaller. That's what we were expecting, of course. And very nicely, you see there's a nice correlation between the two, that as you give more time, you give more essentially opportunity to corrosion to cause the damage. And it's a combination of the two that ultimately leads into failure. So here brings me to the fundamental science of reliability based on entropy. So I just showed you that how entropy, which is as I said, is a measure of damage in our theory or in our vocabulary, essentially accumulates. It accumulates over these paths to this level, which we call is the normalized entropic endurance. Once it reaches this point, Of course, in our case was a tiny crack of 250 micron was observed. At this time, if I take this cut in time, each of these points show how much of a cumulative damage due to amount of entropy I have. So this curve right here shows the distribution of the damage or the distribution of entropic cumulative values of entropy, which is due to the dissipation which are accumulated by that time. So now the area which is the orange, which are the areas which are above the level of entropic endurance, are the causes of failure, are the ones that actually lead into those components that reached this level and cause a crack of 250 micron. And that's the probability that by this time they reach this point. And I would then argue that this probability in this orange should be equal to the probability of the time of failure to the left of this line. If you look at this blue area to the left of the line, then of course that should be equal to this orange area because that distribution based on the definition in reliability is also the probability of failure by this time. So I find the probability of failure through dissipation. I find the same equivalent through the time of failure distribution, which is the traditional reliability models. Therefore, I can correlate this together. I can correlate this F, the failure, the distribution of entropy, and convert them into the distribution of the time of failure, which is G, through this very simple equation that you can see it again. I refer you to this journal paper, which described this equation in more detail, but that's how I convert. And I say that the distribution of time of failure is derived, is the key word, is derived, not found from historical data, is derived from a distribution which has foundation in science. So if you look at now my data here, when I look at the 16 data that from my experiments, these are the time at which I reach this T of C. And if I put a distribution over that T of C, this is the distribution of my amount of entropy which is generated, okay? This is, of course, normalized entropy, and it shows the normalized amount of entropic distribution. And if I go and say that if I now take this distribution and convert it based on the previous equation which I showed you to the time of failure distribution, then I get this red distribution which is derived from my my entropy calculation. And if I take actually these blue data points right here, light blues, which are the time that I reach this micro crack of 250 micron, and if I find a non-parametric, if I put a non-parametric distribution of them, this is the distribution that I actually find for them, okay? So this is my derived distribution. This is the distribution that I derive from my observation of markers of damage. The two are essentially very close, identical. In fact, if you find, if I fit a distribution to those data points, the differences between these two are acceptable from a statistical test of differences. The two distributions are exactly the same, which tells me that this distribution found from this is exactly the same as the distribution from observations of the failure. So this brings me to my conclusion in this talk, which essentially tells that reliability engineering, which essentially historically relied on time of failure from historical data, now can be derived and described through the laws of non-equilibrium thermodynamic, through statistical mechanics, and through information theory. I focused more on the thermodynamic in this talk, but as I said, if any of you is interested further on work I've done on the statistical mechanics and information theory, you're welcome to go and see some more recent publications in this area, which describes that, and they all together are supportive of my claim that reliability engineering is an engineering, sits on squarely on a science, on a physical science, and mathematical sciences. Entropy correlates well with the damage, and ultimately that damage causes failure. As I said, fundamental science, it is a fundamental science of supporting engineering, which now exists. That this theory of damage on the basis of thermodynamics allows incorporation of common and interactive dissipating forces, such as the corrosion damage, which I just showed you, which has been, as I said, a difficult description in reliability in the past. Experimental entropic-based results have provided proof of this claim. And of course, more research is prudent. This is just the beginning. But I think as reliability engineers, we need to do more, rely more on we need to rely more on statistics, but also rely more on physical and experimental researches, so that it shows that it's really a very strong subject and discipline in engineering. So with that, I'd like to thank you for listening to my talk, and I'd be happy to answer any question that you might have.
Thank you, Professor Mohammad Modarres. It was a really great learning for all the people. You can see the number of claps you are getting from so many people. So that's really great, and my salute to you.
Thank you. Thank you very much.
So, sir, here are some questions which I can see. One of the question is from Mr. Anil Amina. He wants to know, can we use this entropic information to model a halt test results? Halt, I'm sure everybody listening knows, highly accelerated live test. So far, we use halt more of a qualitative test. If entropy is true, then even halt results can be used for life estimation. What is your opinion, sir?
At the present time, the halt test or high accelerated life tests are meant to essentially cause failures rather than causing or understanding the process by which that failure occurred. The idea has been to see if there is a way to design out these failures, as opposed to finding what is the source of this cumulative damage or the source of the causes. Having said that, so the data as they stand would not be useful for entropic testing, but I think the machineries that have come out of these halt tests have been very sophisticated, extremely sophisticated, and they allow us actually to do those measurements also ourselves, although in industry, the main purpose has been to really test and get their component out of the field, out of the design very quickly. But I think the equipments have helped us to really do that understanding much better. Yeah, so I think that has been a progress in my mind. And of course, accelerated testing has been a main mechanism by which we can do these days the entropic-based reliability testing. But HALT is a very good tool to do that in the future.
Thank you, sir. Next, I have Mr. Somava Boral. He wants to know how entropy propagates from a damaged component leading to a complete system failure. For example, if a bearing fails in a gearbox, how it propagates and leads to the system failure.
So essentially, entropy is essentially as a measure of that damage. It is not the damage itself. It is a index of that damage, if you will, or a metric that can tell you how much damage you have. From a science point of view, that's how much. Essentially, entropy is a degree of dispersion or chaotic information that you have in your material. So if you have a damaged, let's say, gearbox, you start. It does have at that time an equivalent metric of entropy, and by the time, so from my talk, I can always assure you that by the time that gearbox fails or cracks, it reaches the endurance it has to that entropy. And so if you could measure the dissipation of energy from the point that gearbox has to the point that it fractures, amount of energies which dissipate in terms of heat, in terms of cracks, in terms of all of those that can occur, or amount of wear that it has, you could convert and find how much entropy it has accumulated. So the purpose of this talk was to show you that there is a science behind reliability, but it is not necessarily the tool to predict your, let's say, damage. Still, that the physics of failure or traditional measures of damage are still prime methods of measuring it. These talks are trying to show you that there is a foundation for causing these failures in science. And that is what I was trying to say. But yes, there is, we can find it. In fact, I gave, there was a NSF, U.S. National Science Foundation workshop a couple of years ago at Harvard University. And there were a lot of biologists who came to look at actually. And I was the only engineer that they invited. For some reason, they wanted every aspects of damage to be studied. So these people studied entropy as a measure of damage in biological aspects, and they had come up to the same conclusion that I had come up with, which was saying that all components and units, when it reaches a given level, it has so much endurance to cumulative damage, to cumulative entropy. And when it reaches that level, it breaks. And they had found that actually at the molecular level, at the cell, human organs, same theory applies too. Regardless of what happens, essentially, of course, there is a difference that the cells and organs have an ability to rebuild itself, which means that it could reduce entropy. By that, it means actually it puts energy into the system, which actually reduces entropy rather than, although it dissipates, but it could reduce it. So it has a self-healing concept. We do have that in engineering too. We can do maintenance. That's a self-healing. That means you reduce its entropy, okay? But ultimately, it causes a failure to occur. Ultimately, we cannot add more energy into it. It just keeps adding and ultimately causes its failure. So as I said, this talk was more about showing that reliability squarely belongs into engineering. It's a subject of engineering. All schools of engineering must have it as a discipline. And that was the basis for it.
Sir, time is running out, but I'll just ask one more question from Arpit Srivasu, the last one. There are a few more, but they can do one-to-one. somebody wants to know, can you share some case studies also? That is one. And another question is by Arpit Srivastav. Can we use entropy approach for calculating reliability of electronic components also?
Okay, yeah. So quickly, the answer is yes to all of them. There are case studies. It can be applied to electronics. In fact, it can be best applied to electronics. We have, and I didn't get the time to talk about that. That's a different talk. But I've used this concept in PHM, in prognosis and health management. And the best place to apply it is in electronics, actually, because electronics has the ability to get us easily data by sensors. Sensors are cheap. You can get them. You can get a lot of data out of them, and then use them. So electronic is a prime user of this concept. Actually.
Thank you very much, Professor Mohammad Modarres. So that is the end of the question answer session. So I request Professor Chaturvedi ji or Professor Pradhan to take over. Unmute, Chaturvedi ji, unmute.
Thank you, Commander Jaitley. I saw several questions are coming up, but definitely because of the paucity of time, we are unable to take all the questions. Otherwise, it will be morning, and Professor Modarres will be in the night scenario. So thank you all the audience who have asked the question, and I request Dr. R.N. Rai give a vote of thanks as a last event of this today's last event. Thank you, Professor Rai.
Okay, thank you, sir. So it's an excellent talk, and I was feeling that I'm in a dreamland, you know. However, I would like to extend my heartfelt thanks to Professor Tiwari sir, Director IIT Kharagpur, and Sri Subir Chowdhury, Chairman and CEO ASI Consulting Group, LLC USA, for providing their kind blessings. I would also like to thank Professor retired KB Misra, IIT Kharagpur, an internationally acclaimed academician and library guru and founder of Australian RSC, for his everlasting blessings, and Professor Modarres, Nicole Y. KM, Eminent Professor of Engineering and Director, Center for Risk and Reliability at University of Maryland, College Park, for delivering today's talk as a distinguished speaker. Thank you, sir. I also extend my thanks to Commander V.K. Jaitley, Chairman C-Cube Consultants, New Delhi, and Member Advisory Committee SCSQR, for being a Q&A moderator, and Professor Pradhan sir for his kind presence. Last but not the least, I would like to extend my heartfelt gratitude to all participants and Team SCSQR for their continued support in making this series a grand success. Thank you all.
Thank you.
Thank you.
Thank you.
Thank you, Professor Modarres.
Thank you, sir. Thank you, Professor.
Thank you, sir.
Thank you, everybody.
Thank you so
Thank
much.
you very much. Nice to
Okay.
see you all.
We'll be in touch. We'll be in touch with you.
Yeah, if there is any question also, I'd be happy to answer it maybe.
Okay,
later.
I think for the benefit of the students, I'm curious to know, suppose given an system, you told that the failure perspective, the signs of failure. Now, how to improve the product?
How do we improve the products of the? I think that's a different question though. How would you use to improve the products? Of course, from this concept that I just presented it, the improvement can be for cases where actually from a thermodynamic point of view, it would be that the dissipation of energy. We design materials such that they don't dissipate energy as much, again, from this concept, that if I were to use the hysteresis loop that I was showing, should be the narrowest possible in your design. That would be the way I look at it, for instance. If I'm measuring, let's say, acoustic emissions of the component, it should have basically no significant signals comes out of it. It should be steady. So the designs goes like that. But as I say, these are long-fetched methods that actually can be bring into a practice, but it's the way you can think of it as a scientist, as a foundational scientist. That's the way, when you're looking at it from the point of view of basic science, you don't look at it from a practical point of view, although as an engineer you should. So.
Fantastic. Thank you. I think what you like to say that every tidbit of those components that yeah. Any other thing? Professor Chaturvedi? No, unmute, please. Unmute.
Yes. Anything else? We have completed this session also.
Thank you.
Really happy to have Modarres.
Yes.
Thank you again from IIT. Thanks. Really also I'm thankful to Professor Modarres who immediately accepted our request and giving his talk. Of course, all the audiences. Today, possibly there is a confusion of the link because today we started with the link because the earlier link had certain problems. So possibly because of that, also I am seeing less thickness. It goes up to it around 90 only. So of course we have deleted that earlier link. We are hopeful that the next talk again have 100 plus. This I think we can disperse